In this video, we want to prove that for all vectors x, the p-norm converges to the Chebyshev norm as p approaches infinity. So let's define ourselves a vector x. Then we know that the p-norm of x is equal to the p-root of this big messy sum. And we also know that the Chebyshev norm of x is equal to the biggest absolute value entry of x. And the Chebyshev norm is also known as the subnorm or maximum's norm. It's the same thing. And what we want to prove today is that as we take the limit as p goes to infinity of the p-norm, that we wind up with the Chebyshev norm, which is a pretty wild statement because those two look nothing alike. But we will see that this is actually the case. Okay, so let's start with our proof. First, we define a new variable k, which is equal to the largest absolute valued entry of our vector. Now the next few steps might seem a bit random, but stick with me for a second. First, we are going to take the absolute value of each one of our entries and then we sum them all up. But we know that our value k has to be inside of this sum. And since we are only dealing with positive values here, we know that the sum has to be greater or equal to k. Furthermore, we know that there are n addends in our sum. And since each one of those terms has to be smaller or equal to our maximum, we know that the whole sum has to be smaller or equal to n times k. Note that all of those arguments also work if we raise each one of our terms to the power of p, whereas p is a positive number. If we use sigma notation to clean things up, we can see that the middle term almost looks like the p-norm of our vector x. The only thing missing is that we raise everything to the power of 1 over p. Now we can cancel a few p's, and since this inequality holds for all positive values of p, we can take the limit as p goes to infinity. On the left side, k is not dependent on p, so it just stays the same. And on the right side, we get k times n to the power of 0, so it's also just k. But if our sum is greater or equal to k, and it's also smaller or equal to k, according to the squeeze theorem, that means that our sum has to equal k. If we plug k back into the equation, we can see that we are already done with our proof. We have shown that the p-norm converges to the Chebyshev norm as p goes to infinity. Okay, so let's look at an example. For that, we are going to set x equal to the vector 3 minus 4, 2. We can easily calculate the Chebyshev norm of x by plugging in those entries into our definition. Visually speaking, if we plot our vector x, the Chebyshev norm of that vector equals to the longest segment in that graph, which is in our case the green 4. Let's also plug in these entries into the definition of our p-norm. If we set p equal to 1, we get that the 1 norm of our vector x is equal to 9. Now I'm going to set the number inside of these brackets to 100%. And then we are going to calculate the individual percentages for our other terms. Now let's get bigger values for p. We can see two things here. First, as p gets bigger, the p-norm slowly converges to the Chebyshev norm, as we have shown earlier. And second, as one will expect, the maximum term has the biggest percentage. But not only that, it gets bigger with increasing p's. But on the other hand, we can see that our smaller terms, 3 and 2, become less and less important and slowly vanish from the big picture. But when we neglect those smaller terms, well then we are only left with the maximum to the power of p, and we then immediately take the p-root from it, which only leaves behind the maximum itself, which is the Chebyshev norm of our vector. Okay, and that's about it. I'm going to end the video here before the numbers take up all the space, and I thank you all for watching.